In 1965, Gordon Moore laid down Moore's law. He said that roughly every 2 years, the number of transistors on a microchip will double. For almost 40 years, chips evolved following this law like clockwork. But then something happened in 2006. That's when transistors hit the fundamental limits of physics. So making better chips not only became a lot harder, but also a lot more expensive. That's why today, the solution to better chips might actually be bigger chips. Contrary to what you might believe, the current bottleneck in transistor technology is not size, but communication. Make sure to watch till the end to find out how one company solved this unsolvable problem. This is a human antibody. It's not visible to the naked eye because they measure only 10 nanometers, and they're still 3 times larger than the smallest transistor because the smallest transistor in production today is only 3 nanometers. Today's transistors are nearing atomic scale, and it's becoming obvious that silicone transistors are no longer the viable option. We need something better. We need something bigger. And that's where we start to move from electronics to photonics, which according to the dictionary is a multidisciplinary domain that involves the generation, control, manipulation, and detection of light. But computer engineers weren't interested in photonics as a whole. They were interested in computational photonics, which according to Wikipedia uses light waves produced by lasers or incoherent sources for data processing, data storage, or data communication for computing. Right now, you're probably thinking, isn't light already being used in computing? I personally have fiber optic cables at home which send information using light, and that's where the misconception lies. You see, many people think that transferring information is the same as computing information, but it's not, and it is one of the most difficult problems to solve in computing, or at least it was. Today, there's a little startup that's leading the revolution in computing power called Lightmatter. We all know that light travels. It's the fastest thing we know of. And in the 1800s, the first message was sent using flashing lights and mirrors. And before we could send terabytes of information across the world, we first had to send a simple message. The flashing lights and mirrors were used to send a simple message encoded in flashes. 200 years later, we have fiber optic cables sending vast amounts of data across the web. That's because glass and light are a great way to conduct information quickly. Ever since fiber optic cables were invented in the 60s, you could argue that this was the birthplace of the internet. These cables were grouped together, placed inside a waterproof casing, and laid at the bottom of the ocean. Even today, the reason you can place a video call from America and talk with your relatives in Australia is thanks to these underwater fiber optic cables. They're great at conducting light, and they don't heat up. However, as scientists quickly found out, using light to transfer information is much easier than using light to smash that like button, just like you should if you haven't done so already. But no, in all seriousness, it's much harder to use light for computing power. Think of it this way. Electricity is like a well-trained team of ants building your computer. Light is like a flock of birds. It's fast, beautiful, and powerful, but getting it to work together in a small space, that's the tricky part. Computing photonics is trying to solve this exact problem, but there's a reason light and small sizes don't mix really well. Kind of like my uncle and patron. You could try to pair them up, but all you'd wind up is a disaster. That's mainly because transistors and chips are very tiny, like smaller than a virus. Light, on the other hand, needs space to move around. To guide light, you need tiny roads called waveguides, but shrinking those to fit on a chip without losing the light's energy is incredibly hard. To make matters worse, light doesn't like being crammed into such a small space, which is why scientists haven't been able to use light in computing, and they have had to rely on electricity for this communication. Plus, chips love electrons but hate photons. Computers and GPUs are built to handle electricity, electrons, but light is made of photons, and photons don't naturally talk to transistors. To connect light with the transistor, you need special materials that convert photons into electrons. These materials aren't easy to add to chips without messing up the whole manufacturing process and making the whole thing a lot more expensive than you would want it to be. But Lightmatter seems to have found a way to solve this problem and keep light under control. You see, light likes to spread out in all directions. Inside a chip, it's like trying to guide water through a straw while keeping every single drop from spilling. This requires ultra-precise engineering, and even a tiny mistake can scatter the light and ruin the signal. On top of that, they had to factor in the heat and energy problems they came across. Because even though light doesn't heat up like electricity, the process of creating light on a chip and converting it back into electrical signals can generate a lot of heat. And that heat is a big problem in a packed GPU and for manufacturers. Even though companies are building smaller and smaller chips, which is cutting-edge technology, the manufacturing processes are decades old. They make chips using decades-old techniques perfected for electricity. If you want to build chips that handle light, means redesigning the process almost from scratch. This makes it expensive and hard to scale up for mass production. But Lightmatter has managed to do precisely that. Lightmatter, a startup from Boston, has created a special computer chip that uses light instead of electricity to move data. This approach makes their chip faster and more efficient than traditional ones. Lightmatter's chip uses tiny pathways to guide light signals. These pathways allow data to travel quickly and with less energy. By using light, the chip can handle more information at once compared to regular chips that rely on electricity. In traditional chips, electrical signals flow through metal wires. These wires resist the flow of electricity, causing energy to turn into heat. Light, however, travels through optical pathways without resistance, so there's far less energy lost as heat. Plus, Lightmatter uses tiny lasers or modulators to generate and control light. These components are designed to use minimal energy. As a result, the chip consumes less power overall, which translates into less heat. This design leads to quicker data processing and lower energy use. That's why they've been able to claim that their chips are better than some of the top competitors in the game. Lightmatter claims their chip outperforms top competitors. For example, they say it runs certain tasks up to 10 times faster than leading AI chips from companies like NVIDIA while using much less energy. This speed and efficiency could make it a strong choice for advanced computing needs. This is why Lightmatter's chip could be at the forefront of the AGI revolution. Even if some super smart human built an entire map of human intelligence and how it worked by tomorrow, we still wouldn't be able to translate that into an AGI system. That's because AGI would require enormous processing power to handle the complexity of general reasoning, adaptability, and learning across a broad range of tasks. Today's hardware and software aren't optimized for such demands. This is where Lightspeed's chip comes into play. Lightmatter's chip uses light, which travels faster than electricity, and it can handle multiple streams of data at once. This makes it ideal for the massive and complex workloads AGI demands. On top of that, AGI would consume enormous amounts of energy if run on traditional chips, potentially making it unsustainable. Lightmatter's chip generates less heat and uses less power, which could make running AGI more practical and scalable. And that's not all. AGI requires moving vast amounts of data quickly between different parts of a system. Lightmatter's photonic approach minimizes delays caused by electrical resistance, allowing for faster and smoother data transfers. So, yes, in the future, Lightmatter's chip could become the basis for building AGI, but this could be just one piece of the puzzle. We would still need to integrate different technologies and create advanced AGI algorithms to build a pathway for AGI. For example, we might need to combine photonic chips with neuromorphic chips, which mimic the brain. We will also need to create software that's capable of general reasoning, creativity, and adaptability. Lightmatter's chip is just one part of this complex system, but it could be the backbone on which all of the other components are invented. Here's another video AI enthusiasts loved watching. This is AI Exposed, demystifying the world of artificial intelligence, one video at a time.